Deep in the night sky, stretching across the darkness like a ghostly river of light, lies the Milky Way, our home, our cosmic cradle, the great galactic city whose billions of stars form the backdrop to every story humanity has ever imagined. For centuries, astronomers have treated it as an ancient being, a galaxy born more than 13 billion years ago in the chaotic fires that followed the Big Bang. But what if that assumption is wrong? What if the Milky Way is not the ancient elder we believe it to be, but something far more recent, a cosmic upstart, a galactic newborn whose true age has been concealed behind layers of misleading evidence, observational biases, and assumptions inherited from generations of scientists who never dared to ask the most unsettling question: what if the Milky Way is much younger than we thought? The question is blasphemous in astrophysics. It contradicts every standard timeline, every canonical model of galactic evolution. According to our textbooks, galaxies like ours emerged in the early universe, formed from clumps of dark matter and hydrogen gas collapsing under gravity. They should be nearly as old as the universe itself, but recent findings, subtle anomalies buried in star distributions, unexpected chemical signatures in ancient clusters, and mathematical inconsistencies in the Milky Way's rotational dynamics, suggest something profoundly disturbing. Our galaxy may not only be younger than we assume, but may have formed under conditions unlike anything we have previously imagined. The implications ripple across every field of astronomy. They challenge our interpretations of cosmic history, the processes by which galaxies evolve, and the very role Earth plays in the larger drama of the universe. Consider the possibility for a moment. If the Milky Way is younger, that means the stars surrounding us, the luminous beacons we use to understand the past, may carry memories of events not from 13 billion years ago, but from a far more recent cosmic epoch. Our models of planetary formation, stellar life cycles, and even the distribution of heavy elements in the galaxy would need to be rewritten from scratch. And if the Milky Way formed more recently than other galaxies, then the question becomes unavoidable. What delayed its birth? In a universe filled with ancient galaxies, why would ours have emerged late? Was our galaxy assembled by natural processes that unfolded slowly? Or is something else at work? A cosmic event of extraordinary magnitude that triggered the sudden collapse of primordial matter into the spiral structure we inhabit today? The concept sounds impossible. Yet every major revolution in astrophysics sounded impossible at first. The expansion of the universe was once dismissed as absurd. The idea that stars shine through nuclear fusion was unthinkable. Even black holes were considered mathematical fantasies. And now, a new heresy enters the stage. The possibility that our galaxy is not a primordial entity, but an unexpectedly young structure whose origins could rewrite cosmic history. The mystery begins with unexpected anomalies in the chemistry of supposedly ancient stars. Astronomers classify stars partly by their metallicity, the amount of elements heavier than hydrogen and helium in their atmospheres. In standard models, older stars formed early after the Big Bang should be metal poor. Younger stars should be metal rich, as each successive generation incorporates the heavy elements forged in earlier supernovae. But in the Milky Way's halo, a region believed to contain some of the oldest stars in the galaxy, researchers found something alarming: stars with metallicity far higher than expected for their presumed age. Meanwhile, in the galactic disk, where younger stars should dominate, astronomers discovered a significant number of metal-poor stars that do not fit any known formation scenario. This inversion, old stars with young chemical profiles, young stars that appear chemically ancient, makes no sense in standard galactic evolution models, unless the models are wrong, unless the stars themselves are not the ages we think they are, or more radically, unless the galaxy is not the age we think it is. This possibility gains weight when we look at the distribution of star clusters. Globular clusters, dense, spherical swarms of stars, have long been treated as fossils of the early universe. Many are believed to have formed more than 12 billion years ago. Yet new spectroscopic analyses reveal that several of the Milky Way's clusters may be billions of years younger than previously assumed, with chemical patterns indicating formation in a galaxy that was still assembling, not one already billions of years old. Some clusters even show signs of having formed in external galaxies and later being absorbed by the Milky Way, suggesting violent collisions and mergers may have occurred far more recently than conventional models allow. And then there is the dark matter problem. Our understanding of the Milky Way's gravitational structure relies heavily on dark matter models, which attempt to explain how the galaxy rotates without flying apart. But new high-precision measurements of stellar motion, especially from the Gaia Space Observatory, show rotational anomalies that contradict long-standing assumptions. Some models require the Milky Way's dark matter halo to be far younger than expected. Others imply the halo formed rapidly within a comparatively short time window. The more astronomers refine these rotational curves, the less they resemble the predictions of a galaxy formed in the primordial universe. These anomalies might seem independent, but together they paint a troubling picture. The Milky Way does not behave like an ancient galaxy. It behaves like a galaxy with a complicated, compressed, and possibly much more recent formation history. The question then becomes, what could create such a galaxy? One possibility is that the Milky Way was born from a catastrophic event, perhaps the collision of two or more massive structures that triggered rapid star formation and organized the newly formed stars into a spiral pattern. Spiral galaxies are delicate structures, easily disrupted by collisions. Yet the Milky Way's spiral arms are remarkably well formed and symmetric, suggesting they may not have been exposed to billions of years of cosmic chaos. In fact, the symmetry is so pristine that some astrophysicists propose the arms may be only a few billion years old. But if our galaxy is younger than expected, why does it contain stars that appear older? The answer may lie not in their age, but in how we interpret their chemical signatures. If these stars were formed in other galaxies that merged into the Milky Way relatively recently, they would carry old star chemistry even if the Milky Way itself formed later. This would mean the Milky Way's old stars are not actually born here. They are immigrants, relics of other galactic systems devoured during the Milky Way's growth spurt. Observational evidence increasingly supports this. Streams of stars crisscross the halo, remnants of dwarf galaxies torn apart by the Milky Way's gravity. Some of these streams contain stars older than the galaxy that hosts them. In a sense, the Milky Way may be younger than many of the stars it contains. This is like a city recently founded that happens to house residents who were born elsewhere long before the city itself existed. A galaxy assembled through mergers could easily inherit ancient stars while still being, structurally, a younger entity. The idea that a galaxy can be younger than some of its stars seems paradoxical, but only if we cling to traditional formation models. In reality, galactic mergers, tidal interactions, and accretion events occur throughout cosmic history. The Milky Way may have assembled much later than we think, but built itself out of older components scattered across space. It may have ignited rapidly, forming its disk and spiral arms in a burst of gravitational collapse, triggered by an event we have yet to fully understand. The question grows more profound when we examine the central bulge, the dense, spherical region surrounding the supermassive black hole at the galaxy's heart. Standard theory says the bulge should contain some of the oldest stars in the galaxy, formed early as the first massive clusters collapsed. But recent observations reveal that part of the bulge underwent an intense starburst episode only a few billion years ago, far younger than expected. This implies the bulge is a mixture of old and young stars, a hybrid structure inconsistent with slow, steady galactic evolution. Instead, it suggests sudden reorganization, perhaps triggered by a colossal interaction or collapse event. Then there is Sagittarius A, the supermassive black hole itself. It behaves strangely when compared with black holes at the centers of other galaxies. Its activity cycle appears unusually calm, suggesting it has not experienced the kind of sustained accretion seen in older galaxies. Some models propose that Sagittarius A may have grown rapidly over a relatively short timescale, consistent with a galaxy forming or reorganizing itself not long ago. Taken together, these clues suggest the Milky Way may not be the ancient cosmic metropolis we imagine. Instead, it could be a rapidly assembled structure formed through dramatic and relatively recent events that left behind a galaxy far younger than its peers. But the implications extend even farther. If our galaxy is younger, then the timeline for Earth, and for life, changes drastically. Earth formed about 4.5 billion years ago. If the Milky Way assembled only shortly before that, or reorganized drastically around that time, then our solar system may have formed during a period of galactic instability and rapid transformation. This could explain anomalies in the distribution of heavy elements in our solar system, unusual isotopic ratios in meteorites, and the unexpected abundance of certain radioactive isotopes at the time of Earth's formation. If our galaxy is young, then our position within it, in a spiral arm known as Orion's Arm, might not be a static one. Our entire region may be a product of recent star formation triggered by galactic reorganization. The Sun itself could be part of a wave of stars created during the collapse that formed the current spiral pattern. And that leads to an even more troubling question. Was the Milky Way's formation influenced by natural cosmic processes alone, or is there something more unusual, perhaps even artificial, involved? When we look at the symmetry, the timing, and the improbable coincidences surrounding Earth's emergence, the possibility enters the realm of speculation, yet a speculation rooted in real observational anomalies. If our galaxy is younger, then something caused its formation to occur later than the rest of the universe. What could delay the birth of a galaxy? A scarcity of dark matter, a prior catastrophic event, the gravitational influence of an external structure, or something more exotic, something that implies intention? For now, the mystery remains unsolved, but the evidence is beginning to point toward a startling conclusion. The Milky Way may not be what we think it is. It may be a younger galaxy, a cosmic newcomer formed through processes we barely understand. And if that is true, then our understanding of our place in the universe is about to change forever. If the Milky Way is far younger than we have believed, then its existence challenges not only our assumptions about galactic history, but the very rules we think govern cosmic evolution. A late-forming galaxy should be an astrophysical impossibility. The universe was far more chaotic in its early ages, filled with violent collisions, rapid star formation, and turbulent flows of primordial gas. As time passed, the cosmic engine slowed, raw materials scattered, and available gas grew thinner and harder to compress. Galaxies were supposed to emerge early, thrive through the middle epochs, and gradually settle into quiet maturity as the universe aged. But what if the Milky Way did the opposite? What if our galaxy bloomed late, forming its brilliant spiral arms, central bulge, an intricate distribution of stars in a cosmic era when galaxies were supposed to be winding down? Such a scenario would violate countless models, suggesting either that we have misunderstood the process of galactic formation or that something exceptional happened here, a trigger, a catalyst, a phenomenon powerful enough to compress enormous quantities of material into a structure that should not exist in the present cosmic epoch. And if something exceptional happened here, then the Milky Way may be not just younger, but dramatically different from the galaxies we have compared it to for decades. Astronomers rely heavily on computer simulations to reconstruct how galaxies evolve. These simulations assume that the universe is governed by predictable forces, the slow pull of gravity, the cooling of gas, the expansion of space, and the hierarchical merging of matter. But when scientists run these simulations, the Milky Way always appears early. It always emerges quickly from the primordial soup and grows over time through mergers, accretion, and gradual organization. There is simply no known combination of initial conditions that produces a Milky Way-like galaxy forming billions of years later than expected. And yet, the more we study the galaxy, the more it behaves like a system that defies these assumptions. Much of the confusion arises from the Milky Way's unusual symmetry. Spiral galaxies are notoriously fragile. Even minor interactions with nearby galaxies, small companions, passing dwarfs, or stray streams of material can distort their arms, warp their disks, or disrupt their shapes. The Milky Way should be no exception, yet it displays a level of symmetry that suggests it has not suffered significant disturbances for billions of years. This is deeply problematic if the galaxy is as old as we think. Over 13 billion years, the Milky Way should have been battered by countless collisions and gravitational perturbations. Instead, it looks almost pristine, as if it emerged relatively recently and has not yet had time to be damaged by cosmic interactions. This symmetry is not merely aesthetic, it is structural. Spiral density waves, the patterns that form spiral arms, are notoriously difficult to maintain over long timescales. They require delicate balances between star formation, gas density, rotational velocity, and gravitational resonance. In older galaxies, the arms tend to fade, fragment, or distort, but the Milky Way's arms are vibrant, sharp, and coherent. They appear to be young, active, and well organized. more typical of a galaxy that only recently entered its current configuration. Even the Sun's location is suspicious. Our star sits near the corrotation radius, an unusually stable and safe region where stars orbit at the same speed as the spiral density wave. This protects the solar system from the violent sweeps of star-forming regions that can flood systems with radiation or trigger cataclysmic events. If the Milky Way reorganized recently, the Sun's position may not be the result of cosmic luck, but of dynamic processes that placed it into an unusually favorable location during a recent structural transformation. One of the most puzzling findings concerns the chemistry of interstellar gas in the Milky Way. If the galaxy were ancient, its gas supply should be heavily depleted. Star formation consumes gas, supernovae expel it, and over billions of years, galaxies run dry. But the Milky Way still contains a remarkably rich reservoir of molecular hydrogen, the raw material needed to form new stars. This abundance is more typical of younger galaxies that have not yet exhausted their resources. Some astrophysicists propose that the Milky Way may have acquired fresh gas recently from an external source, perhaps from a massive cosmic filament or from a gas-rich dwarf galaxy that merged with the Milky Way in the not-so-distant past. The most compelling evidence of such an infusion is the Magellanic Stream, a colossal ribbon of gas trailing behind the large and small Magellanic Clouds, two satellite galaxies of the Milky Way. This stream stretches across half the sky and contains enough gas to fuel star formation for billions of years. New research suggests that this stream may not be as old as we thought, and may represent part of a massive inflow of material that recently rejuvenated the Milky Way, effectively resetting its evolutionary clock. If this is true, then the Milky Way is not just younger, it may have been reborn. Rejuvenation events are not unheard of in astrophysics. Galaxies can undergo what researchers call cosmic rejuvenation, where fresh gas triggers new star formation and reorganizes the galactic structure. But such events are extremely rare and usually occur in small, irregular galaxies, not massive spirals like ours. The amount of gas required to rejuvenate a galaxy as large as the Milky Way is extraordinary, implying a dramatic collision or encounter with something enormous. Some simulations suggest that the Milky Way may have absorbed a gas-rich galaxy roughly 8 to 10 billion years ago, far later than expected for such a major merger. Others propose that the Milky Way is still actively feeding on the Magellanic Clouds and may undergo another rejuvenation in the future. But these explanations do not fully resolve the mystery. If the Milky Way formed late or was reborn late, then it should show chaotic scars, irregular motions, disrupted orbits, extreme misalignments. Yet it shows almost none of these. Instead, its structure is nearly perfect. This perfection becomes even more suspicious when we analyze the orbits of stars in the galactic disk. Some populations of stars in the Milky Way move as though they formed in a disk that is only a few billion years old. Their motion is coherent, orderly, and synchronized. Unlike the motion of stars in older disks, which tend to exhibit warps, waves, and irregularities accumulated over billions of years, the Milky Way's disk appears too organized, too flat, too calm. It behaves like a structure that is young or recently reset. Then there is the strange case of the Gaia-Sausage-Enceladus event, the name given to the remains of a massive dwarf galaxy consumed by the Milky Way. This merger is believed to have occurred relatively recently in cosmic terms, and some researchers argue it may have dramatically reshaped the Milky Way, reorganizing its halo, thick disk, and potentially even triggering the formation of its thin disk. If this event happened late enough, it could explain why the Milky Way seems to have two disks, one older and thicker, one younger and thinner. But the younger disk's apparent age is inconsistent with standard models. It appears to have formed too suddenly, too rapidly, and too uniformly to be explained by normal processes. These anomalies multiply when we examine the Milky Way's bar, the elongated structure of stars that stretches across the central region. Galactic bars form through complex gravitational interactions and typically evolve over billions of years. Yet the Milky Way's bar appears to be relatively young and dynamically active. Its rotation rate is faster than expected for a bar of its size and mass, and its orientation relative to the spiral arms suggests it may have formed recently. But perhaps the most baffling evidence of all lies in the supermassive black hole at the galaxy's center. Sagittarius A has a mass of about 4 million suns, relatively small for a galaxy as large as the Milky Way. Most spiral galaxies of comparable size have central black holes 10 to 100 times more massive. This discrepancy makes no sense if the Milky Way is a typical ancient galaxy. Black holes grow over time by consuming gas, dust, stars, and other black holes. If the Milky Way were truly 13 billion years old, Sagittarius A should be far larger than it is. One explanation is that the Milky Way only recently entered a stable configuration that allows material to flow toward the center efficiently. Another is that the Milky Way's central region was disrupted by a major event that halted the black hole's growth. Either scenario implies a history far more dynamic and far more recent than standard models predict. If the galaxy reorganized itself within the last several billion years, these anomalies make sense. If the galaxy formed late, they make even more sense. But if the galaxy formed early and simply evolved normally, none of them make sense at all. This leads to a radical but increasingly compelling conclusion. The Milky Way's formation history may be far from ordinary. It may have undergone one or more events that reset its evolution, reorganized its mass, restructured its arms, replenished its gas, and reshaped its central regions. If so, our galaxy is not a quiet relic of the early universe. It is an active, dynamic, youthful structure emerging from the remnants of older systems. This raises profound questions. What caused the reorganization? Was it a massive merger, a flow of intergalactic gas, a collision with a dark matter structure? Or could there be a more exotic explanation involving unknown forces, cosmic scale phenomena, or processes that challenge our understanding of physics? If the Milky Way is younger than we think, then the story of Earth changes as well. Our solar system may have formed close to the moment when the galaxy itself was taking shape or reshaping itself. The conditions that gave rise to life on Earth may be intimately tied to events on a galactic scale, events we barely understand. The next question is not simply whether the Milky Way is young, but why it might be young, and what forces could have shaped it into the galaxy we call home. If the Milky Way is much younger than astronomers assume, then the truth of its age is not hidden in its luminous spiral arms, its star-forming nebulae, or its bright disk, where new suns continue to ignite. Instead, the answers lie far from the galactic plane, in the sparsely populated halo, a vast, ghostly sphere surrounding the galaxy, home to its most ancient stars, relics of the universe's early days. The halo is traditionally seen as the Milky Way's memory, a kind of cosmic attic filled with artifacts left over from the galaxy's formation. And if the halo's contents do not match what we expect from an ancient galaxy, then the entire timeline of the Milky Way must be reconsidered from the ground up. For decades, astronomers assumed that the halo was nothing more than a dim collection of ancient stars, star clusters, and dark matter, the leftover scaffolding upon which the Milky Way was built. But recent high-precision measurements have revealed something far stranger. Instead of containing a homogeneous population of ancient stars born at the dawn of the galaxy, the halo appears to be a chaotic patchwork, a mixture of populations that do not belong to the same origin story. Some halo stars seem impossibly old, older than many stars in the galactic disk. Others are unexpectedly young. Still others possess chemical compositions that suggest they were born in environments drastically different from anything found within the Milky Way. This discovery alone would be enough to prompt a re-evaluation of the galaxy's history. But the deeper astronomers look, the more anomalies they uncover. Take, for example, the discovery of stellar streams, long, thin rivers of stars stretching across the sky, like cosmic fingerprints left behind by galaxies and star clusters that the Milky Way tore apart. These streams are the remains of cannibalized dwarfs, once independent galaxies now reduced to faint trails of stars orbiting our own. Some of these streams contain stars with ages that do not match the supposed timeline of the Milky Way's formation. If the Milky Way were truly ancient and had been consuming dwarf galaxies for billions of years, then these streams should be thoroughly mixed into the halo. Instead, many remain remarkably intact, suggesting their disruption occurred far more recently than expected. Even more puzzling are the chemical signatures preserved in these streams. Stars from external galaxies tend to have distinct elemental flavors, patterns of abundance that reflect their birth environments. Some halo stars possess chemical profiles so alien that they cannot be matched to any known dwarf galaxy in the local group. Their patterns hint at origins from galaxies that may no longer exist, or from environments unlike anything typically observed in the universe. But what is even more remarkable is that many of these stars seem to have been incorporated into the halo far more recently than standard models allow. If the Milky Way is ancient, then such recently absorbed populations should be rare. Instead, they appear abundant. This leads to an uncomfortable possibility. The halo may not be a relic of an ancient galaxy, but evidence of a galaxy that assembled unusually late, swallowing multiple smaller galaxies in rapid succession. In such a scenario, the halo would not represent the Milky Way's primordial population, but the debris field of a galaxy still under construction, a sweeping archive of the last major cosmic building projects in our region of space. One of the most striking pieces of evidence supporting this interpretation comes from a structure known as the stellar halo break. When astronomers plot the density of stars in the halo as a function of radius from the galactic center, they expected to see a smooth, gradual decline. Instead, they found a sudden break, a shift in the slope of the curve that suggests the outer halo is composed of stars from a single major accretion event. This event appears to have occurred relatively late in the galaxy's history and may have been responsible for assembling a significant portion of the halo. If this is true, then the Milky Way did not form gradually over 13 billion years, but experienced a dramatic growth spurt in more recent cosmic times. The culprit behind this event is believed to be a massive dwarf galaxy, now known as Gaia-Sausage-Enceladus. Its stars exhibit a distinctive sausage-shaped distribution in velocity space, a signature of a major collision. This merger is estimated to have occurred somewhere between 8 and 10 billion years ago, far too late for a galaxy that supposedly formed almost immediately after the Big Bang. Moreover, the collision appears to have been so violent that it reshaped the entire galactic structure, heating the early disk, thickening it, and fundamentally altering the orbits of countless stars. This raises a critical question. If such a major event occurred relatively late, why does the Milky Way appear so undisturbed today? A merger of this magnitude should leave scars, warps, irregularities, persistent distortions, yet the galaxy looks remarkably orderly. Spiral arms flow gracefully, the bar rotates smoothly, the disk shows only minor ripples. It is as though the galaxy has somehow healed faster than it should have, as though it has undergone a process not fully captured by our simulations. Some astrophysicists propose that the Milky Way may possess unusually efficient mechanisms for dissipating energy and restabilizing itself. Others suggest that the merger may have triggered rapid star formation, helping to reorganize the disk quickly. Still others speculate that dark matter played a central role, acting as a stabilizing force that absorbed the brunt of the collision's energy. But there is another possibility, one far more radical. Perhaps the Milky Way's apparent youthfulness is not the result of rapid healing, but because the galaxy itself is genuinely young. Perhaps the Gaia-Sausage-Enceladus merger was not a late disturbance in an ancient galaxy, but one of the formative events that shaped a younger galactic structure. If the Milky Way assembled late, the fact that its components appear well organized becomes far less surprising. It would not have had billions of years to accumulate scars. The halo holds even more clues. Some of the oldest known stars in the universe reside in the halo, so-called population 2 stars with extremely low metallicity. These stars are believed to have formed shortly after the Big Bang, making them older than the galaxy itself if the galaxy formed late. But this is not a contradiction. These stars did not necessarily form in the Milky Way. They could have originated in dwarf galaxies or early mini-halos that later merged to become part of the Milky Way's structure. If the galaxy assembled late, it could have inherited ancient stars from many different sources, creating a halo filled with stars that predate the galaxy itself. This is a profound conceptual shift. It means a galaxy does not need to be old to contain old stars. It merely needs to have collected them. The halo becomes a mosaic, not a reflection of the galaxy's birth, but of its acquisitions. Another surprising discovery concerns the hypervelocity stars, stars hurtling out of the galaxy at speeds exceeding several hundred kilometers per second. Some of these stars appear to be surprisingly old and chemically distinct. Their trajectories suggest they were flung from the galactic center, likely by interactions with the supermassive black hole. But the timing of their ejection events is inconsistent with the galaxy's supposed age. Some models suggest that Sagittarius A, the Milky Way's black hole, may have been far less massive in the past and only grew to its current size a few billion years ago. If true, this would mean the mechanism needed to create hypervelocity stars did not exist in the distant past, reinforcing the idea of a galaxy that took shape late in cosmic history. Perhaps the most striking anomaly in the halo comes from recent measurements of stellar ages using astrophysics, the study of stellar oscillations. This technique has revealed that many halo stars originally classified as old may be significantly younger than previously believed, with ages reduced by several billion years. These revised ages suggest that the halo may contain far fewer truly primordial stars than once assumed. Instead, it may be composed largely of stars that formed in satellite galaxies before being absorbed, again aligning with a possibility of a galaxy assembled late, not born early. But if the halo reveals the Milky Way's true age, it also raises a disturbing question. Why does our galaxy appear to have formed differently than others? Surveys of distant galaxies, snapshots of the early universe, show that spiral galaxies like the Milky Way were common even in epochs shortly after the Big Bang. Yet the Milky Way stands out as structurally unusual, chemically inconsistent, dynamically strange, and evolutionarily atypical. It is too calm, too organized, too perfectly arranged for a galaxy of its mass and age. Some researchers call it a galactic oddball, a structure that seems to have defied the rules of cosmic evolution. If the Milky Way is indeed younger, then this oddness becomes easier to explain. It is not an ancient object that miraculously escaped billions of years of chaos. It is a younger object that has simply not yet experienced the full brutality of cosmic evolution. Its halo becomes a record not of its own antiquity, but of the galaxies it cannibalized during its rapid assembly. This perspective offers a new way to interpret the data. Perhaps the Milky Way is not a contradiction at all. Perhaps it is a sign that galaxy formation is far more diverse than our models predict. Perhaps some galaxies form early, others late, some through gentle accretion, others through violent mergers. In this view, the Milky Way is not an anomaly. It is part of a spectrum we are only beginning to understand. And yet, the deeper one looks at the halo, the more its contents hint at something even stranger, a pattern in the distribution of stellar ages, chemical compositions, and orbital dynamics that seems too systematic to be mere coincidence. Something shaped the halo, something organized it, something influenced the sequence of mergers and accretions that built the galaxy. The question is no longer simply when the Milky Way formed, but what guided its formation, and why. If the Milky Way is vastly younger than astronomers have long assumed, then nowhere is this youthfulness more evident or more perplexing than in the galactic disk itself. The disk is the Milky Way's defining feature, a sprawling, flat, rotating plane of stars, gas, and dust arranged in elegant spirals that sweep outward from the center. It is the region where new stars are born, where the sun resides, and where most of the galaxy's luminous matter exists. But what if this structure, the very foundation of our cosmic home, is not the ancient, stable formation science has taken for granted? What if the disk of the Milky Way is far younger and far stranger than we ever imagined? The galactic disk is traditionally understood as a long-lived structure that slowly forms as gas settles into a rotating plane over billions of years. In this view, the disk should reflect a gradual evolution, older stars nearer the center, younger ones toward the outskirts, and a smooth distribution of ages that traces the slow, steady flow of galactic history. But the Milky Way refuses to obey these expectations. Instead, it displays a bizarre mixture of stellar populations, chemical signatures, and spatial distributions that make no sense in a galaxy believed to be more than 13 billion years old. Start with one of the most startling discoveries of the last decade, the thick disk. Long thought to contain stars that are nearly as ancient as the universe itself, the thick disk was considered a fossil from the galaxy's earliest days, a remnant of the primordial disk that emerged shortly after the Milky Way first began to coalesce. However, new measurements of stellar ages, particularly through astrophysics and detailed spectroscopic surveys, suggest that the thick disk may be dramatically younger than expected. Instead of forming 12 billion years ago, some studies indicate that thick disk stars may be as young as 8 or even 6 billion years old. This presents a profound contradiction. If the thick disk formed relatively late, then what happened during the galaxy's first several billion years? Where is the primordial disk? Why does the thick disk appear to have formed suddenly, as though triggered by a major event, rather than through gradual accumulation? The answer may lie in catastrophic disruption. If the Milky Way experienced a violent merger, such as the collision with Gaia-Sausage-Enceladus, the force of the impact could have destroyed or severely disrupted the early disk. The stars of the thick disk may not be primordial at all, but rather the survivors of the galaxy's rebirth, formed in the turbulent aftermath of a major collision. In other words, the thick disk may be evidence not of an ancient galaxy, but of one reconstructed from its own ruins. Even more puzzling is the thin disk, the region where the sun resides. The thin disk should represent a continuous history of star formation, extending back billions of years. Instead, it displays numerous interruptions, sudden bursts of star formation, followed by extended lulls, repeated cycles of activity that seem to correlate with external disturbances. These cycles suggest that the thin disk did not evolve smoothly, but was repeatedly stimulated, perhaps by impacts of gas clouds, in falling galaxies, or resonance effects from the bar and spiral arms. One particular feature of the thin disk, the so-called phase space spiral, discovered in Gaia data, suggests that the disk has not been in dynamical equilibrium for very long. This spiral pattern appears in the motions of millions of stars and resembles the aftermath of a gravitational perturbation. Simulations imply that this disturbance may have occurred only a few 100 million years ago. If the disk were truly ancient and undisturbed, such a pattern would not exist. Instead, the disk behaves like a structure still settling into its current configuration, a young formation in the cosmic sense. Another inconsistent feature is the warp of the Milky Way's disk. The outer disk is bent upward on one side and downward on the other, creating a warped shape seen in many spiral galaxies. But the cause of this warp remains unclear. Traditionally, warps are explained by interactions with satellite galaxies, but the Milky Way's warp is unusually symmetric and dynamic, precessing like a spinning top. This behavior suggests an external torque, perhaps from the Magellanic Clouds, but the effect seems too coherent, too stable, and too finely structured for a warp that has existed for billions of years. Furthermore, simulations indicate that the warp may be relatively young, forming within the last few billion years at most. A warp this fresh in an ancient galaxy raises new questions. Was the disk reformed after a major disruption? Did the infall of fresh gas reshape it? Or is the warp a signature of gravitational interactions that occurred during the assembly of a young galaxy, not the aging distortions of an old one? Then there is the chemical composition of disk stars. In a galaxy that formed early and evolved gradually, we would expect a smooth gradient in metallicity. Stars near the center should be metal-rich, and those in the outer regions metal-poor. But the Milky Way defies this expectation. Instead, it displays a striking bimodality, a population of metal-rich stars and a population of metal-poor stars coexisting in the same regions of the disk. This chemical dichotomy has baffled astronomers for decades. Now some propose that it may be the signature of a young galaxy formed through merging components rather than gradual enrichment. Metal-poor stars in the disk may not have formed here at all. They may be remnants of dwarf galaxies absorbed into the disk, stars that inherited the metallicity of their original environments. Meanwhile, metal-rich stars could represent populations birthed during intense star formation episodes, triggered by mergers, gas infall, or bar-driven processes. If the Milky Way is younger, this mosaic of populations becomes easier to explain. It is simply the result of a galaxy assembled quickly from diverse building blocks, still sorting itself into coherent structures. Another startling feature of the disk is its flaring, the tendency for the disk to thicken with distance from the center. Flaring is expected in aging disks, but the degree of flaring in the Milky Way is extreme, suggesting that the outer regions of the disk have been dynamically heated. This could occur if the outer disk formed late, from newly acquired gas that settled unevenly, or if it was disturbed by gravitational interactions with dwarf galaxies. In a young galaxy, such flaring would be expected. In an ancient one, it is much harder to justify. The story becomes even more complex when we analyze the rotational dynamics of the disk. Stars in the Milky Way's disk do not rotate in a manner consistent with steady evolution. Instead, they show resonant patterns, wave-like motions, and radial migration behaviors that indicate the disk has experienced repeated disturbances. These patterns are inconsistent with a smoothly evolving galaxy, and instead suggest a history marked by abrupt events, encounters, collisions, accretions that reshape the disk at multiple stages. One of the most surprising findings is the pattern of radial mixing, in which stars migrate substantial distances outward or inward over time. In a stable galaxy, such migration would occur slowly and predictably, but in the Milky Way, radial mixing appears unusually chaotic. Stars have been shuffled across the disk in patterns consistent with strong gravitational influences from the bar and spiral arms, structures that may themselves be younger than expected. The bar, in particular, poses a challenge. Its rotation rate is faster than predicted for a bar of its mass and size in an ancient galaxy. Bars tend to slow over time due to interactions with dark matter halos, but the Milky Way's bar remains unexpectedly fast, suggesting it may have formed recently. This supports the idea that the disk, and by extension the galaxy, is younger than assumed, or at least that major structural components were established far later than conventional models permit. The spiral arms also behave strangely. In simulations, spiral arms tend to be transient features, appearing and dissolving over hundreds of millions of years. But the Milky Way's arms appear unusually coherent and stable. This stability suggests a relatively recent formation, possibly linked to external disturbances, fresh gas infall, or resonant interactions with the bar. If the spiral arms formed recently, the entire disk structure may have reorganized itself in the last several billion years, much younger than traditionally believed. The disk also holds clues in its star-forming regions. The rate of star formation in the Milky Way is surprisingly high for a galaxy of its supposed age. Older galaxies typically show declining star formation as their gas supplies dwindle and their dynamics settle, but the Milky Way continues to form stars at a vigorous pace as though it still resides in a youthful stage. Its gas reservoirs, particularly in the inner disk, show signs of recent replenishment, further evidence that the galaxy may have acquired new material not long ago. One of the most perplexing mysteries is the wave pattern discovered in the vertical motion of disk stars. Gaia data reveals that the disk seems to be oscillating, rippling like the surface of a pond after a stone has been thrown into it. These waves could be the result of a past interaction, perhaps with the Sagittarius dwarf galaxy or another unseen companion. But the pattern appears too coherent, too recent, and too large-scale to fit neatly into standard models. If the Milky Way is younger, these waves may be the lingering aftershocks of the galaxy's formation. All of these anomalies converge on one unsettling conclusion. The disk of our galaxy should not exist in its current form if the Milky Way were truly ancient. Its structure is too organized, its chemical patterns too diverse, its dynamics too disturbed, and its evolution too rapid. Rather than being a relic of billions of years of quiet evolution, the galactic disk appears to be a structure created or reshaped recently, perhaps in a dramatic event that transformed the galaxy from a loose assembly of stars into the spiral structure we see today. This leads us to a profound question. If the Milky Way's disk is young, then the galaxy did not form gradually. It formed through upheaval, through mergers, collapses, infall, and reorganization. The Sun, Earth, and our entire local region may be products of this late-stage cosmic engineering, born into a galaxy that was not a relic but a construction, a place assembled from the remnants of older systems. If the Milky Way is younger, then we are not living in a quiet, ancient galaxy. We are living in a galaxy that recently came into being, still vibrating with the echoes of its violent birth. And if that is true, then the next step is to understand what orchestrated this transformation. Natural cosmic processes alone, or something far more unusual. If the Milky Way is far younger than we once believed, then the clearest clues to this unexpected youth may lie not within the disk or bulge, but far beyond them, out in the galactic halo, a vast sphere of stars, clusters, and dark matter that envelops the galaxy like a cosmic exoskeleton. The halo is a place of contradiction, a realm where ancient stellar fossils drift alongside structures that appear shockingly new. It is where the Milky Way's past is preserved, distorted, and sometimes erased. And if we interpret its mysteries carefully, the halo may reveal whether our galaxy's story is a long, slow evolution or a sudden, violent, recent birth. The halo was once thought to be the most ancient component of the Milky Way. In the classical view of galactic formation, the halo formed first, a chaotic swarm of stars born from primordial gas clouds, later settling into the spherical distribution we observe today. According to this model, the halo should contain the oldest stars, the oldest clusters, and the most chemically primitive records of the galaxy's earliest days. But the halo refuses to behave according to these expectations. Instead, it presents a disordered mixture of populations, some ancient, some surprisingly young, some chemically bizarre, that do not fit neatly into any conventional timeline. One of the most striking anomalies in the halo is the presence of coherent stellar streams, long ribbons of stars traced across the sky, remnants of dwarf galaxies, and globular clusters that were disrupted and absorbed by the Milky Way. These streams are not evenly distributed or ancient. Instead, many of them appear to have formed relatively recently, suggesting that the Milky Way has been actively consuming smaller galaxies within the last few billion years. Some streams are so dynamically cold, so narrow and well-defined, that they cannot have survived intact for more than a few 100 million years. This indicates that the halo is not a quiet, ancient structure, but an active and evolving region, perhaps one still in the process of forming. The halo's most massive known accretion event, the Gaia-Sausage-Enceladus merger, provides a dramatic example. This collision was once believed to have occurred more than 10 billion years ago, but new evidence, including precise age dating of its debris stars, suggests it may have happened significantly later, perhaps 8 billion years ago, or even more recently. If true, this would imply that a major component of the Milky Way was assembled late in cosmic history, long after traditional models would expect galactic halos to have settled into stable structures. It also raises the possibility that the halo's current form, its density profile, and its stellar populations may be products of relatively recent upheaval. Even more perplexing is the distribution of halo stars by age and metallicity. While some halo stars are indeed ancient and metal-poor, others display metallicities too high to have been produced in the early universe. Some halo stars should not exist where we find them. They seem too young, too chemically enriched, too similar to disk stars to be relics of the early galaxy. Instead, they appear to have been ejected from the disk, kicked out by gravitational interactions or energetic events. This blurring of boundaries between disk and halo populations suggests that the Milky Way's structure has been disrupted, stirred, and reassembled. In a younger galaxy, such mixing is expected. In an ancient one, it is harder to justify. The halo's globular clusters present an even greater challenge. Traditionally, globular clusters were considered among the oldest objects in the galaxy. Dense, spherical assemblies of hundreds of thousands of stars formed early in galactic history. But modern observations reveal a more complex story. Some globular clusters appear to be much younger than expected. Others show chemical anomalies inconsistent with early formation. Many clusters exhibit multiple stellar populations, a feature difficult to reconcile with simple formation models. And an increasing number of clusters show orbital characteristics suggesting extragalactic origins. If a substantial fraction of globular clusters were acquired from dwarf galaxies, then the Milky Way's halo is not a preserved relic of its earliest days. Instead, it is a patchwork assembly of remnants from accreted systems. This is consistent with a younger galaxy still building itself from external components. In an ancient galaxy, we would expect far fewer recently accreted clusters and far more native ones. Another anomaly is the halo's dark matter distribution. Simulations predict that ancient halos should exhibit a particular density profile, one that forms slowly over billions of years through hierarchical merging. But observations suggest that the Milky Way's dark matter halo may be more concentrated, more clumpy, and more asymmetrical than predicted. In particular, the central region of the halo appears denser than expected. while the outer halo displays irregular structures that may be remnants of recent infall rather than ancient formation. These features could indicate that the halo did not form gradually, but instead underwent rapid reorganization due to a major merger. A younger galaxy born through this process could naturally possess a halo with the irregularities we observe. The halo's stellar motions also tell a story of disorder. Instead of displaying smooth isotropic velocity distributions, halo stars exhibit distinct kinematic populations, some moving in coherent retrograde orbits, others in radial plunges, still others in swirling patterns inconsistent with early galaxy formation models. These motions hint at a halo shaped by multiple merger events, some ancient, some remarkably recent. If the Milky Way experienced major collisions later than expected, then the halo may still be recovering from those impacts. One particularly intriguing feature is the so-called Virgo overdensity, a massive, diffuse cloud of stars that appears to be the shredded remains of a dwarf galaxy or tidal stream. Its nature and origin remain debated. Some models suggest it could be the aftermath of a merger that occurred only a few billion years ago, a blink of an eye in cosmic time. If such structures are young, then the halo cannot be old and quiescent. Equally puzzling is the Hercules Aquila cloud, another enormous halo structure whose size, composition, and shape defy easy categorization. Its existence suggests that the halo is not in equilibrium, a sign that it has experienced recent disturbances. But perhaps the most dramatic halo anomaly is the Magellanic System. The large and small Magellanic Clouds are irregular dwarf galaxies orbiting the Milky Way. For decades, they were assumed to be long-term companions, gravitationally bound for billions of years. But recent simulations and observations suggest that they may be recent arrivals, galaxies just now falling into the Milky Way's gravitational sphere for the first time. If true, this could have profound implications for the galaxy's youth. The infall of the Magellanic Clouds may be reshaping the halo even now, generating tidal shocks, streams, and perturbations that ripple through the disk and dark matter halo alike. These interactions could even explain the Milky Way's warp, the disk's oscillations, and the halo's asymmetries. If the Magellanic Clouds are recent intruders, they may be the catalysts driving the Milky Way into its current configuration, suggesting we are witnessing a galaxy still settling into its modern form. The Magellanic Stream, a massive ribbon of gas trailing behind the clouds, also challenges our understanding. Its origin remains obscure. Some models propose that the stream is the result of tidal stripping. Others suggest ram pressure from the Milky Way's hot halo gas. But its enormous mass and coherence imply that the Milky Way's halo is dense, structured, and actively interacting with infalling systems, a hallmark of a galaxy still in formation. Even the stellar halo's shape defies expectations. Instead of a smooth spherical distribution, the inner halo appears flattened, while the outer halo is more spherical and structured. This dual halo model suggests separate origins, one formed through early processes, the other through later accretion. The outer halo, in particular, is so irregular, so clumpy, and so clearly composed of accreted fragments that it seems less like the fossil record of an ancient galaxy and more like the active assembly zone of a younger one. One of the most fascinating halo discoveries is the presence of hypervelocity stars. Stars moving so fast they may eventually escape the galaxy entirely. Some are believed to be ejected by interactions with the supermassive black hole at the galactic center. Others may be the result of binary star disruptions during supernova events. But some hypervelocity stars have trajectories suggesting origins in the halo itself. If the halo is producing stars with such extreme velocities, it implies that dynamic processes are ongoing, possibly triggered by recent structural changes in the galaxy. The halo's chemical anomalies deepen the mystery. Some halo stars have chemical compositions so unusual that they cannot be explained by standard models of star formation. Certain stars show signatures of exotic nucleosynthesis, suggesting origins in environments unlike any that exist in the Milky Way today. These stars may be remnants of long-destroyed dwarf galaxies, or evidence that the halo once contained conditions far different from those in the early Milky Way. If the halo's contents are not ancient relics, but the debris of numerous dynamically recent events, then the steady, gradual history long attributed to the Milky Way collapses. Instead, The halo becomes a crime scene, a chaotic explosion of clues, each pointing to a dramatic, disruptive, youthful reassembly of the galaxy. And if the halo is young, then so too is the galaxy it surrounds. The halo's irregularities, streams, mergers, and chemical diversity may be the fingerprints of a cosmic rebirth, a galaxy that did not simply evolve, but was reforged. At the heart of the Milky Way lies an object so powerful, so enigmatic, and so gravitationally dominant that it controls the motion of entire stellar populations, dictates the structure of the inner galaxy, and shapes the very evolution of our cosmic home, Sagittarius A, the Milky Way's supermassive black hole. For decades, astronomers treated this black hole as a fixed point in the galaxy's ancient history, a relic that formed when the Milky Way was young, quietly accreting material ever since. But new observations have revealed a surprising truth. The black hole at the center of our galaxy does not behave like an ancient, dormant monster. Instead, it shows signs of recent activity, signs of recent growth, signs of recent disturbance, signs that the core of our galaxy may be far younger or far more recently transformed than we once believed. If the Milky Way itself is younger than assumed, Sagittarius A becomes one of the most important pieces of evidence. Its mass, behavior, surrounding structures, and explosive past form a roadmap of galactic evolution written in gravitational ink. And when we follow that map, a startling picture emerges. The center of the Milky Way is not the stable, ancient, slowly evolving region predicted by classic galactic models. It is a dynamic, restless, and recently energized core, a core that may have undergone massive transformations long after the galaxy should have matured. Begin with the mass of the black hole itself, about 4 million times the mass of the Sun. This alone is not unusual. Many spiral galaxies host supermassive black holes, but Sagittarius A is notably small compared to the size of the Milky Way. Typical galaxies with comparable stellar mass often contain black holes 10 or even 100 times more massive. This discrepancy raises a profound question. Why is the Milky Way's central black hole so underweight? One explanation is that the Milky Way simply did not have enough time to grow a larger black hole. In older galaxies, black holes grow steadily through accretion of gas, stars, and mergers with other black holes. But Sagittarius A lacks many signs of extended growth. It looks more like a black hole that formed relatively late or experienced long periods of quiescence disrupted by sudden bursts of activity. If the Milky Way is younger, or was reshaped through mergers that reset its inner structure, the modest size of Sagittarius A becomes easier to explain. Even more intriguing is the evidence that Sagittarius A erupted in the recent past with astonishing power. Observations of the Fermi bubbles, two enormous lobes of high-energy radiation extending tens of thousands of light-years above and below the galactic plane, reveal that our black hole experienced a massive outburst just a few million years ago. The energy required to inflate these bubbles is extraordinary, on the scale of a quasar-like flare event, something that should not happen in an old, quiet galaxy. These bubbles indicate that Sagittarius A was far more active recently than previously believed. They may be the smoking gun of a dramatic phase transition in the central region of the galaxy, but the story does not end there. The Erycita bubbles, even larger structures overlapping with the Fermi bubbles, reveal multiple layers of explosive activity. These structures are signatures of repeated energetic events, bursts of radiation and particle jets that shook the galaxy's core millions, not billions, of years ago. Such recent activity suggests a central region still settling from a major disturbance. That disturbance could have been a massive inflow of gas, or a collision, or even the merger with a second central black hole swallowed during a galactic encounter. If the Milky Way is younger, or if its modern form emerged from a recent reassembly, the central black hole's behavior becomes a key piece of the puzzle. Consider, too, the presence of the nuclear star cluster, an extremely dense collection of stars packed tightly around Sagittarius A. This region is chaotic, violent, and full of young stars, stars that should not exist so close to a supermassive black hole. In the classical model, star formation is nearly impossible in such an extreme environment. The tidal forces near a black hole are so intense that gas clouds should be torn apart before they can collapse into stars. Yet here they are, Dozens of massive, luminous young stars, only a few million years old, orbiting the black hole at incredible speeds. Where did these stars come from? How did they form? And why are they so young? One hypothesis suggests that a massive gas disk formed around the black hole not long ago, compressing dense clouds into new stars. Another proposes that a cluster of stars migrated inward from farther out, but both explanations struggle under the assumption of a stable ancient galaxy. In a younger, recently restructured Milky Way, however, the presence of a young stellar population near the central black hole becomes less mysterious. If a major merger or gravitational disturbance delivered fresh gas into the galactic core, rapid star formation could follow, triggering the creation of the so-called S-stars observed today. But the central mystery deepens further. The S-stars orbit the black hole at blistering speeds, some completing full orbits in just over a decade. These stars should be torn apart by tidal forces, yet they survive, and some stars follow orbits that appear remarkably random, inconsistent with long-term dynamical evolution. Their presence suggests a disruption event that scrambled stellar orbits within the last few million years, again implying recent upheaval at the galactic center. Another structure complicates the picture: the central molecular zone, a region dense with gas, dust, and star formation near the core. This region is unusually active compared to similar areas in other galaxies. It forms stars episodically, in bursts rather than gradually, suggesting that it is being fed with fresh gas through irregular or recent processes. These bursts may correlate with disturbances caused by the bar of the galaxy, or the infall of material from the halo and disk. In a younger galaxy, the inflow of gas would be more chaotic, fueling bursts of star formation and activity around the central black hole. Yet another clue comes from the orientation of the galactic bar, a large, elongated structure of stars rotating around the center. Bars tend to form naturally in disk galaxies, but their presence and behavior depend heavily on the age and dynamical history of the galaxy. The Milky Way's bar rotates faster than expected, like a relatively young or recently invigorated structure. This fast rotation suggests that the inner region of the galaxy has not yet reached dynamical equilibrium. And because the bar interacts directly with the central black hole and nuclear region, its behavior provides indirect evidence that the entire central architecture of the galaxy is young. An even more dramatic hint of recent restructuring comes from the so-called X-shaped bulge, a distinct morphology seen in infrared surveys. This structure is typical of galaxies whose bars underwent buckling instabilities, a process where the bar thickens and forms a peanut or X-shaped geometry. Such instabilities occur relatively quickly on cosmic timescales, often within the last few billion years. If the Milky Way's bulge is shaped by a recently formed or recently buckled bar, then the center of the galaxy may have transformed long after its supposed ancient formation. But the central region contains a stranger feature still: the mysterious population of hypercompact stellar systems near the core. These may be remnants of dwarf galaxies torn apart and consumed by the Milky Way. Their presence indicates that the galactic center has cannibalized smaller systems in the recent past. Each of these mergers would have delivered stars, gas, and perhaps intermediate mass black holes into the central region, destabilizing orbits, triggering new waves of star formation, and feeding Sagittarius A. This process resembles not the slow aging of an ancient galaxy, but the rapid construction of a younger one. Perhaps the most compelling clue that the galactic center is not as ancient as assumed comes from the stellar metallicities of stars in the nuclear region. These stars, including the S-stars, show compositions richer than expected for old stars. Many have metallicities comparable to or exceeding that of the Sun, suggesting that the gas from which they formed had undergone extensive prior enrichment, something difficult to reconcile with star formation billions of years ago. Instead, their chemical signatures imply recent formation from gas already cycled through multiple generations of stars in the disk or in accreted dwarf galaxies. Even Sagittarius A itself may not be the first black hole to reside at the galactic center. Evidence hints that the Milky Way may have swallowed at least one other massive black hole in the past, a merger that could have shaken the inner galaxy, ejected stars, and heated the nuclear region. Such mergers leave gravitational fingerprints, hypervelocity stars thrown outward, disrupted stellar orbits, and asymmetries in the distribution of stars near the core. And these fingerprints appear to be present. All of these observations, young stars, recent outbursts, Unusual structures, rapid bar rotation, chemical anomalies, and evidence of past mergers converge on a striking conclusion. The center of the Milky Way is not the quiet, ancient heart of a 13-billion-year-old galaxy. It is the restless core of a dynamic, possibly younger system. A system that may have been reshaped, replenished, or even reborn within the last few billion years. And if the core of the Milky Way is young, then the rest of the galaxy cannot be old. A galaxy's center is its foundation. If the foundation is recent, the structure built upon it must also be recent, or recently transformed. This raises a profound question. If the Milky Way's core experienced massive restructuring, what triggered it? What event injected fresh gas, disrupted orbits, ignited new star formation, and fueled the black hole's outbursts? Was it a merger, a collision, a gravitational encounter with another galaxy, or something more exotic? Whatever the cause, the center of the Milky Way holds the truth. And its truth points to a galaxy that is still young, still forming, still trembling from the events that shaped it. If all the lines of evidence, from the turbulent halo to the restless disk, from the enigmatic bulge to the active central black hole, are pointing toward a Milky Way far younger than assumed, then we arrive at a problem so profound that it shakes the foundations of modern galactic astronomy, the young galaxy paradox. It is the contradiction between what we see and what we believe, between the timelessness we assume and the youthfulness the data suggests, between a galaxy that should be ancient beyond imagination and one that behaves as though it is still forming, still assembling, still settling into the shape we know today. The paradox emerges from a simple question. If the Milky Way is younger than we thought, how can its stars be so old? Stellar populations, after all, are the primary clocks of the universe. Many halo stars are indeed more than 12 billion years old. Some globular clusters appear nearly as ancient as the universe itself. These observations seem incompatible with the notion of a younger Milky Way, but the paradox expands when we consider deeper details. Stars can be older than the galaxy that currently contains them. In a universe where galaxies constantly merge, collide, absorb, and consume one another, a young galaxy can easily be built from the fragments of older systems. In this sense, age is not a single number, but a mosaic. A galaxy can be young in form while ancient in content, like a cathedral rebuilt from stones quarried centuries apart. If the Milky Way was assembled from numerous smaller galaxies over billions of years, its oldest stars could predate the structure we now call the Milky Way, and this is precisely what the data suggests. The halo is a museum of stellar fossils from long-dead galaxies. The thick disk may be the debris of an ancient merger. The bulge may contain stars formed in violent bursts triggered by collisions, and the thin disk may represent the newest, freshest layer, a structure that formed only after the galaxy reached relative stability. Thus, the paradox deepens. The Milky Way behaves like a young galaxy composed of very old stars. And this raises a critical question. Maybe the Milky Way we see today is not the same galaxy that existed 12 billion years ago. Maybe the ancient Milky Way died, destroyed, or transformed by catastrophic events, and the galaxy we inhabit is its successor, a phoenix galaxy rising from the ashes of earlier systems. If so, what could destroy or reset a galaxy? One possibility is a major merger, not a small, gentle absorption of a dwarf galaxy, but a titanic collision with a system nearly as massive as the Milky Way itself. Such an event would shatter the disk, disrupt the bulge, scramble stellar populations, and feed massive amounts of gas into the central region, igniting quasar-like activity. The galaxy would be forced to rebuild itself from the wreckage, forming new structures and re-establishing a stable disk only after billions of years of reorganization. The Gaia-Sausage-Enceladus merger is one candidate for such a reset. But some researchers believe an even larger, still undetected ancient collision reshaped the Milky Way. This hypothetical event, sometimes called the Great Merger, could have occurred only a few billion years ago, wiping out the primordial disk, transforming the halo, reconstituting the bulge, and feeding Sagittarius A enough material to trigger explosive outbursts like the Fermi bubbles. If this great merger happened, then the Milky Way we know, its disk, bar, bulge, central architecture, maybe less than 6 billion years old. This would explain many inconsistencies: the fast rotating bar, the thin disk's wave patterns, the youth of central stars, the unstable halo, the warp, the irregular metallicity distribution, and the numerous stellar streams. The galaxy behaves like something that recently suffered trauma, like something still recovering from a cosmic collision. But the paradox does not end there. If the Milky Way is young, then its environment must also be reconsidered. For a long time, the galaxy's position within the local group was considered stable and ancient, yet evidence suggests the opposite. The Andromeda Galaxy, our nearest large neighbor, is approaching us on a collision course. In several billion years, the two systems will merge, but the key detail is this: Andromeda appears far more massive and far more mature than the Milky Way. If our galaxy is indeed the younger of the two, this difference becomes highly significant. Simulations indicate that galaxies similar to Andromeda tend to cannibalize or disrupt their neighbors. The Milky Way, being smaller and possibly younger, may have experienced strong gravitational influences from Andromeda or other local group members during its formative stages. Such interactions could have triggered gas inflows, disk heating, halo disturbances, and structural rearrangements, forcing the Milky Way to develop later than expected. Even more surprising, recent measurements of the Milky Way's motion through space suggest that the entire local group is not in equilibrium. Instead, it appears to be falling toward a much larger structure beyond its boundaries, a gravitational attractor, possibly associated with the Virgo cluster, or the mysterious Great Attractor. If the Milky Way has recently entered this gravitational flow, external forces could be shaping its evolution even today. The galaxy may be younger simply because it was pulled into a new cosmic environment that triggered fresh stages of development. The paradox becomes deeper still when we examine chemical evolution. The Milky Way's metallicity distribution does not match predictions for a galaxy that has experienced stable star formation for more than 10 billion years. Instead, the patterns look jagged, interrupted, uneven, like a system whose chemical history was periodically reset. Massive infalls of pristine gas could dilute metals. Mergers could inject chemically distinct stars. Starbursts could enrich gas suddenly. This chemical patchwork is inconsistent with a smooth, ancient galaxy, but perfectly aligned with a galaxy rebuilt through episodic disruptions. Then there is the question of dark matter. The Milky Way's dark matter halo seems mismatched to its luminous mass. It is too dense in some regions, too clumpy in others, and too asymmetric overall. These characteristics could result from a young halo formed through rapid, recent mergers. Older halos tend to be smoother, more symmetrical, and more gravitationally relaxed. The Milky Way's halo looks agitated, disturbed, young. The paradox also touches the spiral arms. The Milky Way's arms appear unusually well defined, consistent with density waves triggered in a relatively young or dynamically active disk. In older galaxies, arms tend to lose coherence as the disk stabilizes, but our arms remain fresh, crisp, sharply structured. Their star-forming regions are vigorous. Their dust lanes are prominent. They look like features of a galaxy still in the prime of star formation, not a system that has been evolving calmly for 10 billion years. And the galactic warp, the bending of the disk's outer regions, is yet another contradiction. In ancient galaxies, warps usually decay over time, but the Milky Way's warp is strong, dynamic, and possibly precessing, indicating recent interactions. The Magellanic Clouds are prime suspects, but their status as recent arrivals complicates the picture further. If the Magellanic Clouds only recently entered orbit around the Milky Way, their influence would be a new phenomenon, one capable of reshaping the galaxy in profound ways. But perhaps the most troubling aspect of the paradox comes from comparing the Milky Way to other galaxies. When we look outward at spirals similar to ours, we notice patterns that our galaxy violates. Galaxies with fast bars typically have older disks. Galaxies with strong warps usually result from recent interactions. Galaxies with vigorous star formation often reside in active environments. Galaxies with symmetric, extended halos are usually ancient and stable. The Milky Way doesn't fit neatly into any of these categories. Instead, it displays characteristics of multiple evolutionary phases, pieces of youth, pieces of age, pieces of rebuilding, all stitched together in a puzzling mosaic. This mismatch raises an uncomfortable possibility. Maybe our galaxy never followed the standard path. Maybe the Milky Way is an outlier, a galaxy shaped by unusual events or rare circumstances. Perhaps its youthfulness is the product of coincidences, late mergers, late gas infall, late structural formation, rather than a single catastrophic event. But the more evidence we gather, the less likely this seems. Too many features point in the same direction. Too many indicators suggest recent transformation. Too many signs of youth remain unexplained by ancient models. To resolve the paradox, we must confront another possibility. What if the assumptions of galactic chronology are incomplete? What if galaxies do not age uniformly? What if galactic age is not defined solely by when the first stars formed, but also by when the modern structure emerged? In this sense, the Milky Way could be a young spiral galaxy formed from the ruins of older progenitors. Its stars may be ancient, but its structure, its disk, bar, bulge, halo configuration, gas flows, may be far newer. This distinction between stellar age and structural age may be the key to resolving the paradox. It allows the galaxy to contain ancient stars while still being young in form. It allows the halo to include primordial fossils while the disk is built later. It allows the bulge to form in bursts triggered by mergers. It allows the central black hole to experience recent feeding episodes. It allows the bar to be a fresh feature. It allows the warp to be new. It allows the entire galaxy to be simultaneously old and young. This duality is the essence of the young galaxy paradox. The Milky Way is a galaxy with an ancient soul but a youthful body, a system reborn, not born, a structure assembled from pieces that existed long before the galaxy itself took shape. This view transforms our understanding of galactic evolution. It suggests that the universe may be filled with galaxies like ours, rebuilt, recombined, restructured throughout time. And if galaxies can be reborn, if cosmic structures can rise anew from the remnants of older systems, then what does it mean for the future of the Milky Way? Are we living in the early days of our galaxy's modern life? Is the Milky Way still growing into its final form? And how many transformations still await us? If the Milky Way is not the ancient, quietly aging spiral we once imagined, but instead a galaxy still in its adolescence, reshaped by mergers, fed by fresh gas, sculpted by gravitational forces still in motion, then the final question becomes the most important of all. What future awaits a galaxy that is not yet done forming? What does it mean to live inside a galaxy that is still evolving, still reorganizing, still stabilizing its structures, and rewriting the story written in its stars? To peer into the future of a young galaxy is to confront a universe that is not static, but alive, a cosmos where even the grandest cosmic structures undergo cycles of growth, destruction, rebirth, and transformation. The Milky Way's future, when seen through the lens of youth rather than ancient stability, becomes a story not of slow decline, but of dynamic change. A galaxy that is still forming is a galaxy that has not yet reached its final configuration. Its spiral arms will shift, its bar will evolve, its halo will continue absorbing new streams, its gas reservoirs will be replenished or depleted depending on cosmic tides. Its central black hole will flare, feed, and sleep in cycles. Its stars will be redistributed, its structure may become more tightly wound, or it may unwind again. The future is no longer a smooth, aging curve. It is a landscape of possibilities. To understand where such a galaxy is going, we must first examine the forces shaping it today. The Milky Way is not isolated. It is interacting with its environment on every scale, from the gravitational pull of the local group to the influence of intergalactic gas, from the infall of dwarf galaxies to the looming collision with Andromeda. These external forces are the architects of its future, and as we trace their influence, a picture emerges of a galaxy in transition, still responding to events that occurred billions of years after it should have settled. Begin with the Magellanic Clouds, two dwarf galaxies orbiting the Milky Way that may hold the key to understanding its future. If they are indeed recent arrivals, as new data suggests, then they may still be delivering gas, stars, and dark matter into the Milky Way's halo. Their immense gas stream, the Magellanic Stream, acts like a cosmic river, feeding the galaxy with new material. This influx may fuel star formation in the outer disk or trigger fresh spiral arm density waves. The gravitational interactions between the clouds and the Milky Way's halo may continue for billions of years, reshaping the disk, warping the outer regions, and igniting starburst episodes in the galactic outskirts. But the Magellanic Clouds are only one chapter in the Milky Way's evolving story. The galaxy is also surrounded by dozens of smaller dwarf galaxies, many discovered only recently due to their faintness. These ultra-faint dwarfs, along with the more massive ones like Sagittarius and Fornax, are gradually being torn apart by the Milky Way's gravity. Their stars stream into the halo, forming rivers of stellar debris. Their dark matter halos merge with ours, contributing to its irregularity. Each merger event, large or small, adds structure, momentum, and chemical signatures that ripple through the galaxy. Over the next few billion years, these dwarfs may continue dissolving into the Milky Way, feeding it with new stars and altering its halo shape. This continuous influx means the Milky Way is not approaching stasis, but entering a prolonged phase of restructuring. A young galaxy behaves like a system still assembling itself. The halo will grow more massive. The disk will thicken in some regions and thin in others. The spiral arms may become more defined if fed by fresh gas, or more chaotic if disturbed by infalling satellites. The bar may slow as it exchanges angular momentum with the inner halo. The bulge may evolve as gas inflows trigger new episodes of star formation near the center. These changes will reshape the Milky Way's appearance on cosmic timescales. But for a young galaxy, that is normal. The future of the Milky Way also lies in its relationship with the local group. The gravitational interplay between the Milky Way and Andromeda is slow but inexorable. Andromeda is approaching us at roughly 110 kilometers per second. In about 4 billion years, or perhaps sooner, depending on precise orbital parameters, the two galaxies will collide. But in the context of a younger Milky Way, this collision is not merely a distant cataclysm. It is the next natural step in a galaxy that has already undergone major mergers in the recent past. A young Milky Way may be more resilient to such a collision. Its disk may be more malleable. Its bar may reconfigure or dissolve entirely. Its central black hole may feed intensely, transforming the galaxy into a quasar-like object once again. Its halo will blend with Andromeda's, creating a vast envelope of stars and dark matter. And ultimately, the two galaxies will merge into a single elliptical or lenticular system often called Milkomeda, or the Milkdromeda galaxy. This future galaxy will be larger, more massive, and more stable than either of its progenitors, but its form, structure, and evolution will depend heavily on the Milky Way's current youthfulness. A young galaxy going into a major merger is like a flexible material absorbing force. It bends rather than breaks. But even before the Andromeda collision, the Milky Way's future will be shaped by internal forces. Its central supermassive black hole, Sagittarius A, is unlikely to remain quiet. The inflow of gas driven by spiral arms, bar dynamics, or dwarf galaxy infall may trigger new feeding episodes. These may produce jets, outbursts, and energy bubbles similar to the Fermi bubbles that currently extend above and below the galactic plane. Such events, while dangerous on local scales, help regulate star formation by heating gas, driving turbulence, and redistributing material throughout the central region. In a younger galaxy, such feedback cycles may be more frequent, acting like the heartbeat of the Milky Way's evolution. The future of star formation in the Milky Way is also shaped by this youthfulness. In old galaxies, star formation typically declines steadily as gas is consumed, but the Milky Way's star formation rate remains high, fueled by gas from the halo, the Magellanic Stream, and internal recycling processes. If the galaxy is younger, it may still be in the high-efficiency phase, forming new stars in bursts triggered by interactions and inflows. Over the next several billion years, the galaxy may continue to form stars at a robust rate, especially in the spiral arms and central molecular zone. Eventually, star formation will slow, but the timeline depends on how much fresh gas enters the system. Another consequence of youth is instability. A galaxy not yet settled is more susceptible to oscillations, waves, and structural distortions. The Milky Way's disk is already vibrating, showing vertical waves and radial patterns inconsistent with an ancient relaxed disk. These oscillations may continue, especially as dwarf galaxies interact with the halo. Over time, the disk may slowly settle, but until then, the galaxy's structure will remain dynamic. This instability may influence stellar orbits, planetary systems, and even the long-term movement of the Sun through the galaxy. On an even broader scale, the Milky Way's youth challenges our assumptions about cosmic timelines. If our galaxy is younger in structure, then many similar galaxies in the universe may also be younger than assumed. This raises questions about galactic evolution on a cosmic scale. Are major mergers more common at late times than previously believed? Are spiral galaxies capable of rebuilding themselves long after they should have stabilized? Is galactic formation a longer, more complex process than standard models allow? If the Milky Way is young, it may not be an outlier, but an example of a broader phenomenon, a universe where galaxies have dynamic life cycles, undergoing multiple rebirths across cosmic history. This means that the cosmos is not simply aging, but continuously renovating itself. New disks form, old disks dissolve, bars appear and disappear, halos gain mass, central black holes flare, spiral arms reorganize, galaxies collide, merge and rebuild. In this view, the Milky Way is not an anomaly, but a typical participant in a universe defined by cycles of destruction and creation. And humanity, emerging at this particular moment in the galaxy's development, is witnessing the Milky Way in a transitional phase. We are living inside a galaxy still forming, still absorbing material, still shaping itself, still building new stars and structures. This realization does not diminish the galaxy's grandeur. It enhances it, revealing the Milky Way not as a finished masterpiece, but as a work in progress. Perhaps the greatest implication of all is philosophical. If the galaxy is young, then the future is not defined by decline, but by potential. Our galaxy is not winding down. It is still rising. It has not reached its final form. It is still becoming. And we, as inhabitants of one of its billions of stars, are part of this ongoing transformation. The future of the Milky Way is the future of the cosmic environment that shaped humanity itself. What awaits us is not a static heaven of fixed stars, but a changing, evolving, living galaxy. One that will continue reshaping its own architecture long after our species is gone. And as we study its past, decode its anomalies, and unravel the clues hidden in its structures, we learn that the Milky Way's story is far from finished. It is a story that began before our sun formed, a story that continued through collisions and upheavals, and a story that will carry on through future mergers, starbursts, and transformative events. The galaxy is not old, it is not done, it is not silent, it is alive with motion, energy, and possibility. And in the end, its youth is not a paradox, it is a promise. Thank you for watching. If you enjoyed this video, leave a like and share your thoughts in the comments. Send it to someone who you think would enjoy this topic too. And of course, subscribe and turn on the notification bell so you don't miss the next videos. See you next time.